Right, I'm going to hopefully use this tutorial clip to help explain where the formula for the correlation coefficient comes from. This relates to the correlation chapter from the Edexcel Stats 1 AS module. In the next couple of slides I'm just going to show you things I'm going to hope to cover in this tutorial video. Obviously at any point if you want to read it in a bit more detail you can pause it or you can go back and watch something again. Hopefully by following all these steps all the way through you'll come to a real good understanding about where the formula comes from and how it works. The first thing to do is to make sure that you can remember just the basics of correlation from scatter diagrams. So we've got some pictures here of them and they should give you a general feeling of what correlation is. So when they're lined up like that we have a perfect positive one. When they're kind of a bit more spread out, it's still positive but not as perfect. This one, the dots are all over the place, so that would be described as no correlation. And then the difference between positive and negative is basically a change in the gradient of those lines there. On those diagrams, we were finding out the nature of the correlation just by looking at them, by seeing which way the line sloped, or the general pattern of the points. But it would be great if we could just calculate them, perhaps even without drawing a scatter diagram, and that's what we're going to try and do with this next aim. If I collected a set of data and all of the data was made from two variables, then I could calculate the mean of the x coordinates and the mean of the y coordinates, and I'm going to call that x bar for the mean of the x coordinates and y bar for the mean of the y coordinates. What I then do, which seems like perhaps an odd thing to do, is that I'm going to draw on my graph. I'm going to draw the line where x is equal to the mean of all the x values and y is equal to the mean of all the y values. And that would split my scatter diagram into 4 separate sections. Here's a couple of examples of that. So here you can see, look, the x equals x bar splits it vertically and the y equals y bar splits it horizontally. Okay, and same sort of thing, doesn't really matter whether it's positive or negative. What's really important as well is that it'll always have a central marker in there, so some points will be to the left of that and to the right of that and above that and below that. No matter what my data is, it will always split it into 4 sections. What we need to do next is to think about what would happen or what would be the outcome of any point being in any one of these 4 different quadrants. So for example, a point in this quadrant, how does this point, look at the coordinates for this point, how would they compare to the value of x bar and y bar? And a similar thought, what about the coordinates of a point here? How would its coordinates compare to x bar and y bar and so on? Now you might want to pause the clip at this point just to read this in a bit more detail, but I'll just explain a couple of these points. So if I pick a point, say here, if you look at this point, it's to the right of the x equals x bar line. So that means its x coordinate is bigger than x bar. If I take the mean away from its x coordinate, I'll get a positive value. Also, the same point, if I think about that, and think about the y coordinate of this point, that y coordinate will be bigger than the average of all the y's. So if I take away the mean away from the y coordinate for this one, again I get a positive result. If I times those two things together, because they're both positive, again I get a positive result. If you think about a point over here, say for example, this is going to have an x coordinate less than the mean of all the other x's, and it's also going to have a y coordinate less than the mean of all the y values. So they both give me negative results. And it's this idea of multiplying those values together that's really interesting. So the difference between the x coordinate and the x mean, and the difference between the y coordinate and the y mean. We do that for any point in all 4 quadrants. But what you can notice is in this quadrant here and this quadrant here, when I multiply them together, I get a positive result. And in this quadrant and this quadrant, when I do that same multiplication, I get negative results. So to summarise, I've got them all here in one place. This is really interesting. This shows that if I have points in this general alignment I get positive values, and in this general alignment I get negative values. And up to now we've just thought about one point at a time, but if I have a whole series of points all over the place and I add up the outcome of that calculation for each one of those points, the general total that I get from these will give me an indication as to how they're aligned. The layout of the points, if they're mostly in this arrangement here, then I would get a generally positive outcome by adding those things together. And if they were aligned in this general arrangement, I'd get a generally negative outcome by adding them all together. And if you think back to our correlation, positive correlation and negative correlation. This thing here called SXY, this is exactly that. This is saying for all the points on my scatter diagram, I would sum the value that you get when you times the difference between its x coordinate and the mean of the x's by the y coordinate and the mean of the y's. And doing this provides me with the positive or negative value. And this is what describes the nature of our correlation. So we said that SXY tells you whether it's positive or negative, but what would be great is to be able to say, well, how good a correlation is it? Is a really strong relationship, or compared to other relationships, is it actually pretty meaningless, pretty weak? So what would be great is if we could find a fixed scale so that all correlations could be compared to each other. To help illustrate my point, what I've got here is I've got some examples of scatter diagrams, and my thought really was I wondered if you'd be able to decide just by looking, just by eye, which of these has the strongest correlation. Have a little think, and in a moment I'll reveal the answer. Right, that's the shocking thing really. They were all exactly the same piece of data, and the reason I showed you that is I just wanted to make the point that it can be affected by all sorts of different things, and judging by eye might not be a great idea. Hopefully you can realise that just by changing the scales on the axes, or even using different units to measure the variables, it makes the scatter diagram look really different. And that was the danger of it. If you were looking at the scatter diagram and trying to use that to judge the strength of the correlation, if it can be affected by simple things like this, then that's a risk. So when I do these calculations, the x coordinate take away the x mean and the y coordinate take away the y mean, I can get really different results depending on what units I've used to measure x and y. And what I mean by that is, if one of my variables was, say, I don't know, length, then I could use millimeters, centimeters, meters, inches, miles, whatever, and I'd get really different numerical answers from those calculations depending on the units that I've used. What's good for us though is there are things we can do, and these steps that I'm about to show you will remove the effects of the size of the values from the calculation of the strength of the correlation. So it's really important that we understand that. Calculating the strength of the correlation shouldn't have anything to do with the size of the units and the values that I obtain from doing these particular calculations. Just to recap, whether or not I get positive or negative correlation is determined by SXY. When I calculate SXY, I do get a number though, and it is a product of these calculations here. You know, I'm multiplying these together, so I will get a number, and I'm interested as to whether it's positive or negative, but this number could be changed drastically by the units that were involved. However, if I divided by the size of that, it would remove the effect on this on the final calculation. The same thing would really happen is if I divided by that value there. That would take away the size of this from the final calculated number. So again, SXY, this provides me the positive or the negative element of my correlation. I'm just now trying to figure out a way of making it so that my correlation is measured on a consistent scale. Doesn't matter what it is the variables are, that I can always see the correlation will be between -1 and 1. We really want it so that the only way I can get a negative value is through the outcome of this SXY calculation. That means if I am going to do some division to scale down the size of the number that I get, I really need to make sure I don't introduce some extra negative signs. So these things cannot really affect the positive or negative value I get from here. One thing that you've seen before to actually do this is to basically square something and then square root it, and then that guarantees you've got a positive value to work with. So this is what we arrive at. This at the top here, this is the calculation we had for SXY, and this was the area where I could get my positive or negative value. And these bits on the bottom here, they're just mechanisms to make sure that I get a positive outcome for this and a positive outcome for that, and that when I'm dividing by them, all they're doing is scaling down the size of this so that it falls between 1 and -1 again. And just as there was an easier way of writing this as SXY, then these calculations inside these square root bits, they can be written more easily SXX and SYY. And there you go, that explains what they are. Now our next ambition for this tutorial was to help you see that there's a couple of different forms that you can use to calculate this correlation coefficient. And it's a bit like with the standard deviation formula, and if you go back earlier on in the statistics module, you'll remember that there was a couple of ways of doing them. One way was to go from raw data and you calculated differences and squared them and then took an average and then did square root. Or there was another way that involved you understanding these sigma notations. Now these are the different sigma notations for the elements of the formula you saw. They're provided in the formula book in your exam, and if you're lucky you get a question where you literally just substitute the summary values into these expressions. So again, to revisit this formula here, so R, this is called the product moment correlation coefficient, and this is a measure of how good a correlation is. This can only ever be between -1 and 1, and we should be able to move on to interpreting this in the next couple of slides. Just to, one last time, just take a good look at this. So this one, SXY, this can be positive or negative. This tells me about the type of correlation I've got, so that I can compare the strength of one particular correlation with another example. This bit, all of this division, is a mechanism to make sure it lives within this scale, and the square rooting of it is to make sure that the only way I get positive and negative values is through that bit on the numerator. So here we go then, this is how we can begin to interpret the outcome of this calculation. And it's pretty obvious, I think, once you've seen these things, and I bet you've probably suspected it. Thankfully, a value of 0 means there's no correlation. It's really important that you think about it being a linear correlation, because that's all this calculation does. It tells us how well these points line up. Now, just because they don't achieve a straight line doesn't mean there isn't a relationship between the variables, but 0 means they don't look anything like a straight line. Right, and these other two options, positive 1, that's perfect positive correlation, and -1 is perfect negative correlation. And I hope it's obvious to you that you could get any sorts of values in between. You get 0.7, 0.8, minus 0.2 or anything like that. So if we return to these particular diagrams from earlier on, we should probably be able to guess some sort of correlation values for these particular pictures. I'd expect perfect positive correlation to be 1, and perfect negative correlation should be -1, and no correlation should be 0. And then these bits in between, well, we could sort of argue about this a little bit, but it doesn't really matter. This might be something like 0.8, and this would be minus 0.8. Just to give you an idea, I mean, it's reasonably strong, and it shows the positive or negative values. Right, one of the last aims of this tutorial video was to help you work around coding, and coding is something that you've seen throughout the Statistics 1 module, Coding is basically a way to try and make your calculations simple. So if, for example, you were doing a correlation coefficient work and all of your numbers were something like 5001, 5007, 5011, 5003, all your numbers had this 5000 but were actually not varying significantly, you might just want to take that 5000 away and make it so you're working with smaller numbers. I think most of us would agree that working with smaller numbers is an easier thing to do, and coding is a mechanism to allow that to happen. So you can swap your original variable x for one called p by taking something away and dividing, and same for this, you can swap your original variable y by taking away something and dividing. The really brilliant news about product moment correlation coefficient is that doing this coding doesn't make any difference to the value you obtain for R. And really we shouldn't be surprised by that, because we've just seen how the way R works, the way the calculation is built, it's designed to remove the effects of the units. And actually doing this coding, you're essentially just changing the units. And if the units don't make any difference, then of course that shouldn't affect the final answer. Right, so I set out to explain a couple of things with this tutorial video. I wanted you to be able to tell if a relationship exists. Sometimes that's as simple as looking at it on a scatter diagram, but now you know how to calculate whether or not there's a correlation. You can calculate whether it's positive or negative, and you can calculate the strength of it. So first of all, we did it along these lines, so looking at it on a scatter diagram to see if there was any correlation, and then this one about the nature of it, calculated by considering means. That was the basis of our SXY calculation. So how does each point compare to the mean of the x's and the mean to the y's? And so that we can compare correlations, it'd be really helpful if they were always on a fixed scale and it didn't matter what units you used. So that's what we tried next. And we saw that by doing a division, we managed to get the scale between -1 and 1. And we needed to make sure that we didn't introduce any false negative bits to our calculation. So there's a squaring and square rooting bit that makes sure that I don't get any negatives. Now, really quickly, I showed you that there was alternative forms to calculate the correlation coefficient, and I should also point out again that these are available in the formula book that you get in the exam. I spoke ever so briefly about how you interpret these. So, 1 is perfect positive correlation, -1 is perfect negative correlation, and 0 is no correlation, and you get all sorts of values in between. And the last and really simple thing was, okay, you might want to do some coding so that the numbers you're working with are smaller or easier, but the best thing about it was it doesn't make any difference to the value of the correlation coefficient you obtain. I hope that's explained where that formula comes from, and now you'll go away and practice actually using it. So I hope best of luck with that, and good luck with the rest of your studies.